Okay, modeling exponential functions. So just a reminder that with exponential functions, it's the letter, or sorry, rather the number that it's attached to x that's base. Okay, so this guy right here is going to be that base. If that base is bigger than 1, you've got exponential growth, and it is going to grow very, very quickly. The bigger the number, the bigger the growth. Exponential decay is when you've got a fraction of some sort, maybe 1/2, 3/4, things like that. Again, the smaller the fraction, the quicker that decreases as well. What we're going to focus on is a couple of general formulas that deal with exponential growth and exponential decay. The first one is just your general exponential growth model. You got a couple letters there. A is the initial amount. It could be dollars if you're dealing with money. It can be a population like we're going to deal with here in a little bit. R is going to be your rate. Now make sure you change that percentage into a decimal. Time is time in years. Sometimes it's a little bit different than that, but for the most part, it's going to be time is in years. And then that 1 plus R piece is going to be your growth factor. So the population has grown exponentially at a rate of 5% in West Fargo. So there's your R, 0.05. In 2018, the population was 35,000. So there's going to be your A, your initial amount. What will the population of West Fargo be in 2022? Let time be the number of years since 2018. So if I were to write a exponential model, so an equation that I can use for any situation, it would look like y equals 35,000 1 plus 0.05 raised to the x power. Now, this is called a growth factor because, look, I've got a number that's bigger than 1, albeit just barely bigger than 1, but it's going to be bigger than 1. And if I want to figure out the population in 2012, I'm going to put in for x my time, which is going to be 4 for 4 years. Okay, so the part I'm going to do is in the parentheses, so 1.05. I'm going to raise that to the 4th power, and then I'm going to multiply it by 35,000, and that gives me a population of 42,542.7, so maybe I'll round it up to 43 people. So that's exponential growth. There are other exponential growth models. This one is particular to just interest and compounding interest. You've got P for principal, that's the amount that's invested. R is going to be your rate as a decimal. N is the number of times that it's compounded per year. And T is going to be your time in years. So here we've got our principal of $500 goes into an account that pays out at 3%. We're going to find the balance after 2 years, so time is going to be 2. And we're going to figure out what that looks like after different types of intervals of n. If it's annual, your n is going to be 1. So you're looking at 500 times 1 plus 0.03 over 1. And that's going to be 1 times 2. Now, this is where the other model could possibly work, because if n is 1, that decimal is not going to change at all, and that time is going to stay as 2. So again, I'll go 5.03. I'll raise that to the 2nd power, multiplied by 500, and we've got $530.45. If it's quarterly, that n is going to change into 4, so now it's 500. 1 plus 0.03, but now it's divided by 4 because of quarterly, and it's going to be 4 times 2, or the 8th power. So now I would make sure, I would take the 0.03, divide that by 4 first, add 1 to that, raise it to the 8th power, multiply it by 500, and I get that to be $530.79, which probably rounds up to 80 cents, but a little bit better quarterly than it was annually. Now, monthly, that means n is going to be equal to 12, so we'll take 500 at 1 plus 0.03 to the over 12, and 12 times 2, 24th power. Same thing, I'm going to take that decimal 0.03, divide that by 12, add 1 to it, raise that to the 24th, multiply that by 500, and I get $530, and it looks like about 88 cents. So just a little bit more. So the more it compounds, the more money you're going to make. Okay? Compounding continuously, so over and over and over. You're going to use this formula that says A is equal to P with an ERT. Now that E is a number. It's actually the number 2.718. It's on your calculator. And like the tip off to use this formula is the fact that you've got interest that compounds continuously. So you've got your interest rate of 2.5. You've got a principal of 5,000, and now you've just got 1t for time. Your amount is going to be that 5,000. Okay, and if you want, you can just go ahead and use 2.718. There's an E button in your calculator that you could use, and you're going to take your rate in decimal form times 2 as your exponent. So 2.718 raised to the 0.025 times 2, okay, times 5,000. And this time I got $5,256.33. That's how much money I would have in 2 years if that compounded continuously. And continuous is the word that you're going to look for in a problem that says, hey, ding, 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 ding. I need to use that formula. Okay, exponential decay, A, R, and T all stand for the same things that the growth model had. It's just that 1 minus R is now your not growth rate, but your decay rate, okay? How fast they shrink. So it talks about the amount of Y in grams for this sample of iodine 131 after T days is followed by the following equation. It starts off at 50. Now, how do I know that? Well, because that A there is the initial amount, or what I could do is I could put T is equal to 0 and figure out that, hey, this decimal of 0.92 to the 0 power turns into 1, or 50 times 1, I'm going to end up with 50 grams. What percent of the substance is left or decays each day? Well, I'm going to take my growth concept of 1 minus R and set that to 0.92. I'm just reasoning this out, but if I got 1 and I want to knock it down to 0.92, that means that 0.08 must have been my R, or an 8% decay. Okay. An adult takes 400 milligrams of ibuprofen each hour. Why? The amount of ibuprofen in a person's system decreases by about 29%. Write a model for this. So Y equals the initial amount, which is the 400 milligram, 1 minus the 0.29, the rate of decay, raised to the X power. Okay, if I want to figure out how much milligrams is in a person's system after 3 hours, I'm going to take 400, 1 minus 0.2, and that's what, let's see, 7.1, and I'm going to raise that to the 3rd power. So, okay, multiply that by 400, and that means that they're going to have 366.2 milligrams of this ibuprofen in their system after 3 hours.